And please stick around with us. This is our last 30 minutes. I hope that's okay if everyone can stick around. We have 30 more minutes and we want you until the end because we're going to ask you questions about the course at the very end. So please stick around if you can. We're here until the long end. And yes, go, Koustubh.
Thank you, Justine, and thank you everyone for staying with us. Please know that we will be exceeding our time today, but yeah, call it our poor planning or whatever, but this is how it's going to be. Okay, so with the now we will get into a slightly more complex scenario, but a more real life scenario. And what do we do in those scenarios? And these will address some of the questions that we've been having from some of you over the past few days since we started. Now, you might all recollect this example from Sarichat. You might also see visually when you're looking at this map right in front of you that there is that the snow leopard abundance seems to be non-uniform. It is not the same. If I randomly create, where are the boxes? Yeah, so if I randomly create boxes across my study area, I won't always count the same number of activity centers. You see, in some cases I have one. Over here, I end up with a huge number of snow leopards. Here I capture much less. Here I capture much less, and so on. So there is a variation that we are seeing. In other words, the density does not seem to be uniform in this case. What do we do in this case? So we have, again, I will start slowly. We'll set up 56 camera traps. Here again, what I've done is, because I knew there is a possible variation that could happen. And a lot of these hypotheses have to be set a priori, or at least during the study that you are setting up. It gets very difficult to collect the data and then try to data mine. We should try to avoid that as much as possible. Anyway, so we set up these 56 cameras in roughly two grids. One of them is over here, as you can see, with about 30 cameras, another grid here with another 18 cameras. And then I had some extra cameras left over. Sorry, these are 16 cameras, these are 30 cameras. The remaining 10 cameras, I set them up kind of randomly, as you can see, some here, some here, some here, there's over here, 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 and so on. You can notice these little cameras. I'm sorry, the colors are not very clear, but I believe you should be able to have a look at them. Now, one of the best parts of spatial capture recapture based analysis and designs is that you don't have to worry about putting two cameras too close to each other or making areas where you have no cameras in between. Like over here, you see there's no camera in this area, right? That's okay. Between these two cameras, there is a huge gap. And that's something which SECR, not SECR, but spatial capture recapture is pretty robust to. In conventional capture recapture, we could not leave these areas. We could not leave these areas. They were called as holes, and there was no way you could have left holes there. But in spatial capture recapture, you can have, like, these two cameras are just 2 kilometers from each other. These two cameras are only 1.5 kilometers away from each other. So you can end up not oversampling, but having 1 or 2 additional cameras in some areas just because you find a very cool site. If you put them too close, like less than 0.5 kilometer, then they will both represent the same camera, and that won't be useful. Try to keep them further away from the resolution that you will use ultimately in your mask. If they are further from the minimum resolution that you're looking at, that's reasonably fine. Then each of them will get assigned to a different camera trap. But technically speaking, you can have a design which is variable and does not have to be absolutely spick and span and uniform as was expected earlier. So when we set up these cameras, let's say this is how they look like, the red dots, and then we have created a buffer around these traps. So you see this little buffer out here, that's the buffer of 15 kilometers. a mask that we have just created, building about 15 kilometers. You can see the mask here, make.mask, and at 15 kilometers, and we create this mask over here, buffer of 15 kilometers. Everything is the same. You might remember this is the code we were using earlier as well. So we create a mask around these cameras, and this is how it looks like. Now, a very important step now is to provide it with some spatial data about habitat. Now, in our case, what we do is we basically export, once we have created the mask, we export it to a CSV file. From R, we export it as a CSV file, which is a comma separated variable, which can be opened in Excel or any ArcGIS, any GIS program. We can use QGIS, you can use ArcGIS. If you're good with R, you can even use R-based GIS packages as well. A lot of people prefer to do all of this work within R. You are free to do that. There's no harm in doing that. What we've only realized is that it usually is much slower for some reason to do some of these spatial analysis, spatial manipulations on data in R, which is why we export it to a GIS tool. So on any GIS tool, this is how you can preview the habitat layer. You can see the blue one is the protected area, the green one is the non-protected area, and the red one is the hunting concession. Now, what I'm going to do is, and this is how you can see it on a QGIS or ArcMap tool. What you can do is you can create, once you have exported the mask as a CSV file, you can import that on a GIS application, and then you can add the value of protected area or hunting concession or unprotected area for each of these little pixels here. So each of these little dots, will eventually get a value, whether it is a PA, like these will be all HC, HC, HC. This one here will become a PA. This point will then become a non-protected area, and so on. And of course, these areas will have no value because they're outside our mask, right? So you will end up with a value for each of your pixel on your GIS tool. And then what you do is you basically export it again as a CSV file and then import it in R using this very simple tool where you say Sarichat mask with covariates. You have to read a mask from the file, which is called this one. Just call a header true, because on top there will be one layer which defines which column stands for what. Now that's a bit of a clunkier, clunkier method. There are other methods of doing that within R, but with some large data sets, especially the one that I mentioned from Nepal and from Pakistan, we've realized trying to do this entire covariate creation within R at times can take several hours and sometimes even gets hung. So maybe we were not doing it the right way. So maybe that's our shortcoming, but it can take time, which is why it's easiest for us at least to just do it on a GIS tool and bring the values back. Now, once you bring the values back, what you end up with is something like this. In this case, you can see the covariates are listed here. Protection, and there's one more covariate which is called distance from settlement. What this is, we'll talk about it later. But we have protection status and we have distance from settlement for each pixel on the mask. And the X coordinate, Y coordinate, just ignore these for now. All these three values, just don't worry about them. But X and Y are the spatial coordinates. Please remember, SECR only works with projected coordinates, and that too typically or preferably in meters. If you don't have your data, if you have your data in latitude, longitude, you will have to project it into a UTM or world Mercerator. But if you try to analyze it within the latitude, longitude data sets, it will not work. SCCR does not have the ability to transform data on the fly. You have to do it. There are tools within R where you can do it. So that should be one of the easier ways of doing it, or you can do it elsewhere on a GIS tool and bring it back as well. Anyway, so once you have, you can always check the covariates of the Sarichat mask here, and you can also use plot to plot the covariates. And when you see, when you plot them, they look something like this. You basically have your camera traps listed as it is, and you can see these values taking different colors. Red stands for hunting concession, green stands for non-protected, and blue stands for protected. Now, this particular map I have used with a slightly different tool, but if you do plot, very similar output can be generated that you can see right here. Now, what we will be doing is we have to test a hypothesis here that my density is not constant. I'm testing a hypothesis that my density is different for protected areas, it is different for unprotected areas, and it is different for hunting concession. I might want to test that my density is different in hunting concession versus all other habitat also. Whatever is your hypothesis, you have to create a column defining that. In this case, our column, which is defined by protection, denotes what is that value the protection is taking, and we are going to test whether density is a function of protection. And to test that, you remember the first one, which is in the red square. This is the model we had earlier run, right? We had earlier used spiti.large.hhn. We can do the same thing with Sarichat here instead, and leave everything as it is. In our case, what we are now using is, we are using this particular model where we are, the only difference you see here is this one. We are saying that density is a function of protection. So protection, the status of protection, and there are three values there, you remember? One of them is protected area, one of them is non-protected, and one of them is hunting concession. So basically we are telling it that there could be three possible values that it will take. And all of that, because protection is defined as a factor, it will automatically take care of it. We're just defining density as a function of protection. Everything else remains the same, right? Everything else remains the same. The mask here should have this protection as a column. That's a very important point. If you don't have protection listed as a covariate column in your mask, then this function will create an error. But if it is there, then it will just run very smoothly. It'll take a few seconds. It'll take a little longer than it has taken the previous models, which assumed constant density, because now we are modeling density as a function of yet one coefficient. And what we get is something like this. Now, this is very similar to what we looked earlier. The only difference here, you look carefully, is that instead of D, now there are three coefficients that we are looking at. There's not just one coefficient like was the case in the earlier one. Now we have these three coefficients. What do these mean? You remember we discussed density, the coefficient, the relationship of density with the coefficient to be D is equal to exponential of beta of density, which is this one, right? That's what we had looked at. So this was it. Now, all we are doing is we are saying density is still an exponential function of a constant here, but in addition of a function of whether the beta or whether the mask point is a protected area or a national park. Now, what happened to the hunting concession? In very simple terms, what you can see here is if an area is a protected area, then PA's value will be 1, but national park will be 0. if an sorry, not with not protected will be 0. If an area is not protected, then BPA will be 0. The value of PA will be 0, but the value of not protected will be 1. And if both of these are 0, then automatically it is a hunting concession. Now this is how they use it for a limited degree of freedom. If you have 3 covariates, you basically you have 3 categories in a covariate. You define only 2. The third one is automatically estimated as the residual. Now in this case, what we are seeing is the density is a function of some constant, which means that if both of them are 0, then the density would be this much, which is automatically, if it is not a PA, not a national park, not an unprotected area, then it is automatically going to be a hunting concession. If it is a protected area, then the value would be a sum of these two, because the third one will be 0. In fact, I have an example where I'm doing this. It is here. One common error a lot of times we do is that of using predict to estimate density when my density is non-uniform. If you do that, the function will still run. It won't create an error, and it will give us some value, but this value would be the estimated density of one of the corners, whether it's this point here, I don't remember, but it will be the density of one of the cornermost pixels. That's all it is going to estimate. It is not estimating the average density of the whole study area. So you should not, ideally, you should not use the predict function if you are estimating any of the 3 parameters as a function of one or more covariates. So you don't use that. Instead, to estimate density, you can use this function here, which is the function we just discussed. Now the value of a P, whether it's a PA or a national park, how do you calculate this? It's like this. The coefficient beta, the beta coefficient was minus 9.96 in the previous slide. The coefficient of a protected area was 1.34. I just multiply it with 1, and what I get here is my, similarly for hunting concession, I just make both of these 0. I just say exponential, oops, that's the wrong one. Was it the wrong one? Yeah, this is wrong, sorry. My mistake, yeah, this is wrong. It will just be minus 0.996, and the third one would be this one, right? For not protected. And when you estimate these, I don't know why I left that error there, but when you estimate these separately, these 3 equations you solve, you get the density of snow leopards in a protected area to be 1.83 snow leopards per 100 square kilometers. Density of hunting concession of snow leopards in a hunting concession to be 0.47 per 100 square kilometers, and density of snow leopards in national parks to be in not protected areas. This little area, see, this is the only area that is of interest right now. We don't know what's happening here. Don't say that that density applies to other areas as well. We only know about this little part only. And in the not protected area within the study region is 1.09 snow leopards per 100 square kilometers. Now, what it does is, if you look at this carefully, it's actually this value. So this value was being estimated at this little corner, somewhere in the unprotected area. And if you use this value as the overall density, then you're going to underestimate it. So one reason why I wanted to clarify and re-emphasize, do not use the predict function if you have used density as a function of one or more covariates. Now, what about density? So how do we estimate density? It's a very easy or a slightly convoluted way to do that. You estimate the overall abundance from your study area by region.n, and you divide it by the total mask area. That's all you need to do. Once you do that, you will end up with the density, average density of 1.25 snow leopards per 100 square kilometers. What you can also do, which is another fascinating opportunity here, is that if you are interested in knowing the density, let's say there is a small, I should change the color. Let's say there is a small protected area here. In fact, let me clear it here. Let's say there is a, no. Well, actually this was anywhere protected area, but let's say there is a core zone within the protected area. Now we are interested in what is the snow leopard density of this core zone. I can estimate that by giving it a little smaller mask here in my analysis. Instead of region region dot over here, I will define a new mask and I can estimate that abundance. But anyway, what it's telling us right now is the overall density of snow leopards in the whole study area is 1.25. And if we compare it with the other estimates, it's slightly different. Now, the question arises, which one to use? Am I supposed to use the one which is assuming constant density, or am I supposed to use the one which is using density as a function of covariates? In this case, one covariate, which is distance from, which is protection status. What you see over here, we have a very smart tool which is called Akaike Information Criteria. This tool provides, it basically estimates the likelihood of a model to be close to what our data is explaining versus the cost of adding additional parameters. And it basically balances them out. So it's almost like when you're eating a biryani or a pulao, you will have there has to be a balanced a combination of rice versus meat. If you put too much of meat, then it's not a biryani, it becomes more like kebab. If you put too much of rice, then it's just rice with a little bit of a few pieces of meat. You have to have that optimal balance. And what it does here is, for every new parameter added, it penalizes the AIC value so that you don't keep, because if I add just too much of too many parameters, my model will keep getting more and more likely to be to have a better fit, but then that's not replicable. It's not what we really want. We need to have a clear balance between the number of parameters added to a model versus the fit that it is generating. And AIC, or AIC for small area, corrected AIC for small samples, are very useful tools that balance it out. Now, in this case, what it defines is, you will see the minimum AIC value in this case is 553 for the model which uses density as a function of protection. What it's basically saying is, and if you look at this AIC weight, you will notice that it has 82% weight, or 0.82 is the weight, whereas the weight of this null model, which assumes density to be constant, is 0.17 or 17 or 18%. What it says is, out of the models that we have tested, which is these two models, the first model, the one where density is assumed to be a function of protection status, has 82% more weight or more chances of being, or has 82% better fit, or it explains the data variation 82% as opposed to 18% of the null model. So it's not saying that this is the best, this is all that you should use. It's saying that the truth is somewhere in between, but it's very heavily based by, or it's very heavily weighed towards the density as a function of protection model. So it's very likely that your study area, you do have density as a function of protected area, but there is still 17 or 18% chance that it may not be true. So that's how you need to look at that, that it might be constant. So that's how we can weigh these. And in typical world, in an ideal world, you use the models with the minimum AIC value. If these values are pretty substantially different from each other, then it's very straightforward to use them. In some cases, if they're very closely separated, like if your AIC weights are 0.43, the second model's AIC weight is 0.37, and so on, then you do another process called model averaging. We'll not be talking about it, but there are very simple tools available to do that. And ultimately, your estimated abundance you use. In this case, because our AIC weight for the density as a function of protection is higher, we will use this model estimate, which are different, but not that different. You see, if I was using the null model, I would have overestimated my density by about 6 individuals or 5.5 individuals. I would have just said that in this whole area, there are 6 or 7 more snow leopards than what they are. Now, it is a bit of a bias, but it's a bias that you might at times be able to live with. In fact, if you had a few more camera traps in the other areas, not everything set up in this high density area, you might have actually realized that the overall estimates would have become very similar to 0.69. So if we had enough camera traps in the hunting concessions as well as the non-protected areas, or we would have just set up camera traps randomly, you would have ended up with a very, very unbiased and a very close to real estimate, even without using covariates. So that's where you need to at times, yes, it's important to look at covariates, but don't kill yourself over it. And many times people end up listing like 50 covariates, which are almost virtually impossible to be tested. So think as an ecologist, think as a scientist or as a natural history person about what is it that could be affecting the snow leopards and what is of interest to us. Now, a snow leopard might be looking at hundreds of parameters while making decisions. We don't need to emulate snow leopard. We have specific questions at times, and that's where you might want to use these covariates. Otherwise, design-based inference, which means a fair estimation of density from a gradient, should be good. A situation may occur where you may have not just one covariate, but more than one covariate. In this case, in this particular scenario, we are exploring whether density is a function of the least cost distance from hunting camps. Now, there are hunting camps or settlements around this protected area. So does the snow leopard population avoid humans? If that is what I have to test as a hypothesis, I can create a function. I mean, this one was the first null model, if you recollect, the very basic model that we tested. This was the second model that we tested. Now we can test density as a function of least cost distance from the settlements or human or anthropogenic activities. I can also go further and test a function of both distance from settlements and protection as well. So there's with just 2 covariates, we end up with now 4 combinations, and you can create several such combinations. Ideally, one shouldn't look at every possible combination. This is where one needs to make an informed decision of what combinations we are looking at, what could be of value in a particular case to snow leopards. And then, of course, I mean, the more the covariates you add, the likelihood might improve, but at the same time, it will keep getting penalized by AIC. So at some point in time, the AIC will start, even if it is a better likelihood, the AIC will start complaining, you're going way too high, too many parameters with very little improvement in the model fit. And that's where automatically they go down. They become less valuable, or less, the weight becomes less for the modeling process. Next. Okay. So that was density. We have a last little segment, about 5 more minutes left here, which is where we have another particular scenario where now we are using 2 types of cameras. Now, let's say I'm using a high quality camera and a low quality camera. A high quality could be one of the better makes of cameras. Low quality could be one of those cameras which someone just donated and I still want to use them, but I know they're not very good at detecting movement, so they don't always trigger even when the animal moves in front of them. In earlier designs, you could not use such a variable trapping grid. In spatial capture recapture, you can. In fact, what you can also think about these blue and red dots, blue dots denoting low quality cameras and a red one denoting high quality camera, is think about them as locations. Now you might have some very good locations where there's a lot of snow leopard movement, so they are high quality sites. And then you might have some poor quality sites which are either on a slope, and you just had to set up a camera because you wanted to cover a certain region. You couldn't find a very exciting location, but you had to put up a camera. So you can have a location. You can have another scenario where you have some cameras on ridge lines, some cameras in valley bottoms, some cameras on slopes or cliffs. Each of them are likely to have a different encounter uh, if those points happen to be the activity center. In other words, if I have a camera, a high quality camera, let's say for simplicity's sake, on a high quality camera, if it is at the activity center, I'll have lots of encounters. But if I have another camera right there, which is of low quality, it'll just miss out a few encounters. So instead of, let's say, 3 encounters at the activity center, with a poor quality camera, I might end up with just 1 or maybe less than 1. One in like half an encounter, or maybe 2 encounters in per camera trapping session. Now, in such a situation, what you do is you need to add a covariate to your to your trap data. Now, your capture data remains as it is. There is no change in this capture data, as you will notice. Nothing is changing here. All we are saying is, wait a sec. Yeah, okay. All we are saying is that that there are some cameras which are high quality and some cameras which are low quality, right? So C4 is low quality. Okay, most of them were HQ in this case. There are other cameras. So actually, you can see the table here. I have 38 cameras which are high quality and 18 cameras which are low quality. Look at the encounter rates. On HQ, on the high quality cameras, I have 132 encounters of snow leopards, whereas on low quality camera, I have only 7 encounters, much less proportionately as well. Proportionately much smaller number of encounters on low quality camera. So there seems to be something that's bothering the encounter rates or the detection probability per se, and we need to be able to test it in this scenario. What we do is, now what we are doing is we are modeling lambda 0, which is encounter rate at activity center, as a function of quality of the camera trap. The quality can be anything. Please no quality can be topography, terrain quality, camera trap quality, or whatever. Anything that you think is affecting the type of or the ability of your particular camera to detect snow leopard given its presence around it. And when we run this, where is the model? Yeah, so these are the previous 2 models where we had estimated, assumed density to be constant, lambda 0 to be constant, sigma to be constant. And there was another one where we tested density to be a function of protection, but lambda was constant and sigma was constant. Now we are testing a model which we are calling sarichart.hhn lambda L0 as a function of Q. How do we define it? We define it, density is constant, lambda 0 is a function of quality. That's all. Now, where is this quality listed? The quality is listed in our trap data. Okay, so it has to be somewhere. So quality is listed in the trap data. So any covariates which are testing sigma, which are testing lambda 0, should be there in our trap file as trap covariates. So when we use these covariates here, yeah, okay. We run the analysis, we run the SECR.fit, and we come up with this output. Now, density here, we have assumed it to be constant, but you see the density's value has changed a little bit. In this case, now look at the lambda 0. The lambda 0 is now taking 2 possible values. One value when lambda 0 is low quality, in which case it's saying minus 2.05 is the beta of lambda 0 LQ, and Otherwise, it is, so when it is not low quality, then lambda 0 HQ is 1.086. Now, clearly you can see what's happening here. In any simple words, you can just say that, if it is low quality, the lambda 0 is less. If it is H quality, it's positive. Now, this is a very simple way of saying that your detection probability at the activity center is going to be much higher for the HQ cameras than it is for the LQ cameras. And that's how we basically define this function or the outputs of this function. And when you look at the outputs, you will see that I don't know why I kept using the Spiti large. It's actually the Sarichat model, which I should have just copied. I forgot to copy the right model here. But you know, I mean, everything is the same. Right, here it is. Okay, so you see the model output okay. Oh, this is the third type of model. Sorry. Now what we do is we also additionally test density as a function of protection and lambda 0 as a function of quality. So I'm not only saying that I have more encounters on high quality cameras, but I'm also worried that maybe the density is also not constant. Density is also probably varying. Who knows? So I'm testing two hypotheses simultaneously. And when I do that, what I end up with, how do I model it? I call density as a function of protection, lambda 0 as a function of quality, and the output looks something like this. This is the previous model. We're not looking at it. You see density, again, very similar to what we did earlier, and lambda 0, these two values here. So what they indicate in this case is they indicate that that there are these again. So they basically indicate that in this particular model, we are saying that density is variable, and we are also saying that lambda 0 or detection probability is also variable. What happens in this case is when you compare it with the other three models, you will realize, again, use AIC to test the hypothesis that which of the three models is valid, or I wouldn't say valid, which of the three models is best describing my data. And when you do the AIC table, you create the AIC table, you will end, what we ended up here is with a model which says that has almost 65% chances of, there is 65% better explanation of the data as opposed to the one which only considers lambda as a function of quality, lambda 0 as a function of quality. I should have listed another fourth model, and it would have been somewhere in between. But in simple words, all this is saying is that it is very likely that our density is a function of protection status of the landscape, and the encounter rates are higher on high quality cameras as opposed to low quality cameras. And both these scenarios are technically true because we have simulated them in a way that they happen to be true. So in this case, we knew we were the gods of this particular universe that we created. But in real life, you can bring in such covariates and test them. There are other ways of bringing in variations because of the status of a snow leopard, male, female, breeding class, and so on. And they could affect sigma. So you can bring those there as well. The only saving grace there, and the only reason why we don't often end up modeling those, is because when you are sampling, you're not sampling in a way that only males will get captured or more males will get captured than females. If you're sampling in a nice way, you will end up with almost the same same impact or the same effect on all, or there will be no real bias in your sampling for males or females only. If there was a particular case, let's say you were putting cat lure, then you're only attracting males, for example, on that particular cat lure. Then you would need to bias, you would need to incorporate that that function where your sigma, you might end up with more males and fewer females camera trapped, in which case you will need to model for the variable effort. And in those cases, there are means to even model sigma exactly the same way as we just showed how to model density and lambda 0. Okay, so with that being super late, beyond our time, I'd like to stop here. And please let us know if you have any questions. Just to let you know, we will have, I think we will have the Google group running for a while, so don't feel too pressured to ask a question right now if you want to take time. And then we will also be sharing these presentations and videos. Justine has been sharing those. Yeah, sorry, Justine.
No, no, don't be sorry, Koustubh. That was really great. Thank you more than anything. I had someone in the background, and they were like, wow, this guy knows his stuff, clearly. So I think it clearly shows a really good explanation. And thank you, Koustubh, and thanks, everyone. If I can just ask, before we go into questions, Koustubh, can we do a poll on the course? And then we'll go into questions. If you have time, we can stay for
Sure.
like 10 minutes extra
Sure,
for questions.
definitely. Yes.
And then
yes.
everyone can leave if you don't want to stay for questions. But we'd like just to keep you for a final poll related to the course, because this will really help us for future courses quickly.
Just one point, Justine, before I forget, is that all the work that we have shown right now, you must have seen this, the analysis right now. Everything we're going to provide you with in an annotated R script. So I might just want to show you here. Just in just one more minute, I won't take as much as I've
forgot
done.
about that. This is important.
Yes. So basically what we have done is we have, if you can see my screen, I hope you can see my screen.
Yes, yes, we
can
see it.
The entire work that we have done in the last 4 sessions, 8 hours, entire work, including those single animal movements, multiple animal movements, gummy bear experiment, Sarichat example, Spiti example, all of this work is done on these 2 scripts that we will share with you. The second script we will provide you with will be a little more ready-made for you to run spatial capture recapture. We will be providing you with the simple data sets that we have created, and you can run the analysis yourself. Each step we will have it nicely annotated. If I can show you where those lines are. Sorry. Where did those go? There. So each step we have annotated what a particular step does. Like here we are saying create first column as session 1 of for all. In this case, create second column, create third column. So you will have very detailed explanations of each step that goes on here. And if you can just run this script from top to bottom, you don't need to download any additional data. Just the script is all you need. And just at one point, you will need to import from a right folder. That's all you need to do. You will be able to run the entire analysis and the visualizations that we have shown here. So it'll take us about a few more days to complete this annotation, but then we'll be sharing this with you, and you should be able to reuse these scripts for any analysis that you would like to do. Having said that, please know that the purpose of this workshop was not to develop ourselves as analysts, but to understand how spatial capture recapture works. For detailed analysis, if that is of your interest, then we have other ideas, and Justine will be talking a little bit about that in her questionnaire as well. But the purpose of this workshop was to be introduced of what SCCR does, how it does it, and how it can be valuable. And then if you are interested in learning detailed analysis, then there are other workshops that we can help organize or even point you to. Yeah, so okay, with that, I'll shut up now.
No, that's great. That's really important. Please use the script, our script, everyone, and try it out if that's of interest to you. But like as Koustubh said, this was really an attempt to also help plan and think about planning surveys. We're always there to support analysis later on. And often you learn from analysis, you can also learn from doing. So we believe, you know, it's nice to support you guys through your own data analysis, and then you get into these more detailed understandings.